Okay, everybody, welcome back for day number 3. We are officially starting again. And by popular demand, special request, a little review of normalization for this morning. For those people who are curious about it, we do have 2 questions, actually 3 questions. One of them you actually have to look at a couple of tables and decide what you're going to normalize out of it. If we could keep the volume down, that way I won't feel like I'm competing with the crowd. Long story short, I'm going to review normalization now, just to benefit you guys, because you'll have to do this on the final, and then you'll also have to answer some questions about tables that have issues in them that are related to normalization. So, I know I've gone through this lecture already once before. I'm not going to get the same review of it. I'm going to use this as kind of a visual aid to point out a few things and to remind you of a few things that I did go over. So I'm going to give you a summary of what it is we looked at. This lecture is number 6B if you're looking for something to study, and it goes through the normal forms of first normal form, second normal form, and third normal form. So what I'm going to do is take a few minutes and tell you, well, what characterizes first, second, and third, so you can figure out what you're doing in each one of the steps, so you can figure out what the problems are. You do not have to identify that something is in first, something is in second, something is in third. Everything is in first, second, and third if it's in third. So, so technically I wouldn't ask you a question of that nature. Instead, what I'm primarily interested in doing is, do you know where the problems are? Do you know what problems are characteristic? So if we take a look at this, we look at simple data. This is a first normal form. Well, this is actually a report. First normal form is fairly easy because first normal form, we just turn it into a table. It's first normal form because we have repeating groups. So we have here project name Evergreen, Amber Wave, Rolling Tide, and Starflight. I don't know what this data is about, but anyway, we have some project names. And then we have some blanks in here. And the blanks in here are really coming from this concept here. Somebody took a report. This usually happens, actually. A lot of people take Excel spreadsheets and they put them into Access or they put them into Oracle. They just build a table with everything in it. And they end up getting a kind of a database representation of a spreadsheet because they don't know the difference. They think it's the same thing. Generally produces a first normal format for us. So in figure 1, it doesn't handle data very well. It appears to work because you can print it out. But here's the conversion to first normal form. To actually put it into first normal form, we would take the repeating, we still have repeating groups, but we have to fill in the data. Because if we sort this differently, we don't know John G. News, he's a database designer. We don't know what project he's on, or project name, or project number. So we have repeating groups, and this is the characteristic of the repeating group phenomena. It's like when it's all the same. That's when, because it doesn't contain a key or anything, it just contains all the same stuff. So repeating group derives its name from the fact that the groups of the multiple or related entries can exist for any single key attribute occurrence. So the project number, we have the project number and the project name occurring repeatedly for multiple records in the particular relation. So it must not contain repeating groups here. Technically, the repeating group looks like this. We get rid of the repeating group by filling in the information. And we put it into first normal form at this point by supplying 15, 15, 15, 18, 18, 18, 20, 22, 20, 25. We still have the repeating groups, but at least we can use it from a database perspective. This isn't really technically in first normal form yet. This is still a spreadsheet. So, and I wouldn't spend too much time worrying about first normal form because nobody can really want it in first normal form. We all want third normal form, really. So normalizing the table structure would reduce these data redundancies, and then normalization is a 3-step procedure. So step number 1. So here's your note-taking part, and this is the part I really wanted to cover as a review for the final this afternoon. Step number 1, eliminate those repeating groups. So present the data in a tabular format where each cell has a single value and there are no repeating groups. So eliminate the repeating groups by eliminating the nulls. You fill in the information. Make sure that each repeating group attribute contains an appropriate data value. So as I mentioned before, we have repeated information, but we have technically removed the repeated groups by filling in the blanks. So now we have 15, 15, 15, evergreen, evergreen, and we have it all filled in correctly, hopefully. And then, so now this is actually first normal form. So if I showed you a table listing that looked like a spreadsheet that had repeating groups in there, it wouldn't even be in first normal form. This would be first normal form. Is it really that useful to us? No, we can make improvements on this as well. So let's make some improvements. In step number 2, step number 1, which is normal form version number 1, doesn't have any keys, but we have some repeated information, but we have entries for everything. We got rid of the nulls, we got rid of the spaces. In step number 2, we're going to identify the primary keys. So identify the primary key. Primary key must be uniquely identifiable attribute value, and the new key must be composed to be put in the table. So step number 3 is identify all of the dependencies. So the dependencies, so step number 2 is let's look for some primary keys. And then let's look for the dependencies on those primary keys. So a dependency can be dictated with the help of a diagram, a dependency diagram, or entity relationship diagram. So when we create entity relationship diagrams, we take the diagrams, we translate them into tables. We create 2 or 3 normal form tables, where the goal is to create a third normal form set of tables, because the entity relationship diagram is supposed to eliminate the problems of the lack of the keys and the lack of, well, the repeated groups that are fixed and some of the other problems that are part of the design that can be removed if we followed a proper entity relationship diagram. So the goal of entity relationship diagramming is to create third normal form. We could end up with a second normal form. Just because we create that diagram doesn't guarantee us third normal form. We could have a second normal form. So in terms of identifying all the dependencies, and when we get between 2 and 3, we're looking at partial dependencies and transitive dependencies. So it's all about the dependencies, and it's all about the keys. So the first is pretty easy. So the one I'm going to give you on the final, it might be a first, might be a second, might be a third. But it's more interesting to look at second and thirds. But there may be a first normal form problem in there as well. So all you have to do is basically look at the data, and you'll see something is going to pop out at you when you look at it. You'll go, "What? These tables are weird. What's wrong with these tables?" And then you'll figure it out, hopefully. Because I'm going to give you some tables, actually, some table structures, a couple of them, and you'll look at them and you'll say, what's the problem with this? Which is why we're reviewing this. So identifying all of the dependencies so they can be depicted by the help of a diagram. And the dependencies are found within a given table structure. And we have dependencies. Dependencies are good. We just don't want partial and we don't want transitive. So let me talk about those two in a few. Get you a bird's eye view of the relationships of the tables, makes it less likely or an important dependency may not be overlooked, as an example. So here's our first normal form table that contains both problems. We have partial dependencies and transitive dependencies. And yes, those are problems. We don't want them. These are issues that you'll be looking at. So a partial dependency is here. We have a project number, as remember before I said 18, 15, those were that first column was those project numbers. The second column was the project name that goes along with the number. Well, there's no requirement that says that that name has to be the same for all of the 15s. We filled it in to make it the same, but we could have project 15, Evergreen, project 15, Evergreen Valley, project 15, Evergreen _ Valley 1. We can have different names. If we can have different names for project 15, we have what's called a partial dependency. They're all 15s, but the corresponding data that goes along with that key or with that data is partial. There's only part of a relationship. It's not 100% that everything is going to be called the same thing. That's really the definition of a partial relationship, where there's a relationship, but I belong to group 15, but I'm not called the same thing. I'm called something else. So we have partial dependency. If we had a full dependency, every single 15 would be identified by the same exact name, Evergreen, or whatever it was called. There would be no variations at all. There would be no changes with that. And then we have here project employee number. Well, the employee number is we have partial dependencies between, we have 1, 2, 3, 4 different problems with this table. we have 3 partial dependencies and 1 transitive dependency. So just to identify the other partial dependencies, we have 2 key values in here. We have employee number and project number. Well, that's a partial dependency because we don't necessarily have to have a particular employee number to be working with a project number. And so we didn't identify them as separate keys, by the way. This is all one table. We also have a partial dependency with the employee number and the charged hours. We could have different hours being charged to the same employee. Actually, this happens sometimes when they don't classify jobs and stuff. We also have a partial dependency between the employee name and the job class. And we also have the, when there's not a strict rule that says something has to be something, then we have partial dependency. We have full dependency when there's a strict rule that says job class XYZ makes this amount of money an hour. And every time we use job class XYZ, every single employee makes that same amount. That's a full dependency. When one employee can make another, same job class, they can make this amount, another employee can make that amount. Partial dependency. They're still in that job class, but they're making different amounts. So that's what makes it partial. Transitive dependency means one determines the other and the other determines the other. So the job class determines the charged hours and the charged hours determine the job class? Well, yeah. One determines the other, so you can't tell, and then they're dependent without using a key. There's no key, which also makes it transitive. And I have some formal definitions I'll go over in a few minutes just to review this again, to give you the finite definitions. But that's what we're looking at in terms of the structure in this particular example. We're going to fix all of these problems in a few minutes. So the first normal form, all the key attributes are defined. All the attributes are in the table. There are no repeating groups in the table. All attributes are dependent on a primary key. Yes, they are. It's the project number on the far left-hand side, or it's the employee number, depending upon how we want to look at it. All the relational tables satisfy first normal form requirements. This is just one example that we're looking at. All of the other tables in the database would also fit these requirements. And some tables contain partial dependencies. That's okay for first normal form. And dependencies that are based only part of the primary key. Meaning it's using the number, but the descriptions are different. And then sometimes used for performance reasons, but should be used with caution. Actually, that's a good point. For performance reasons, if you don't want to join all the tables together, you could make a pretty decent first normal form table, but you're required to know that all of the employee project names are spelled a certain way. So when you put it in, you have to make sure that you're putting in the project name correctly, and you're putting in the job class correctly, and you're putting in the right amount of hours. So you're not allowing the database to provide you the referential integrity. Instead, you're doing it manually. But you're still subject to data redundancies. You can still have the same key in there twice. In fact, we have 15 and evergreen in there 4 or 5 times. So let's make this and put this into second normal form. If we put it into second normal form, we have 2 steps we go through because we have to remove the dependencies. So we have this relational database design that can be improved by converting it in 2 steps. Okay, first step, identify all the key components. We have multiple keys in that table. Identify the multiple key components. First normal form, we're looking at a primary key, just one key for the whole table. And second, we're looking at multiple components that might actually be part of the key relationships. Write each key component on a separate line, and then write the original composite key on the last line. And then each component will become a key in a new table. So really what characterizes second from first is the division into multiple tables. We're taking it out. In fact, if you did the normalization activity, you did this. There's an assignment, if you haven't noticed, on database normalization. Gives you 1 or 2 tables. I think I give you 1 table, or maybe 2 tables, I'm not sure. And then you take and you create like 5 tables from that. There's 4 or 5 tables that come out of that, because you got to pull out all the partial dependencies. You shouldn't have partial dependencies. If you're in third normal form, you don't have any partial dependencies. Everything is, you have one single primary key for each table, and each table should hopefully, if you're not going to get rid of transitive relationships, you're going to have a foreign key in there too to link it together. If you do that, I can't remember exactly off the top of my head. I'm thinking there's like 4 tables at least that come out of that assignment. So 4 or 5 tables. Did you come up with 5? I believe the solution has 5 in it, actually. So if you've done it, you didn't have 4 or 5 tables, then you might want to rethink that assignment. Okay, so identifying the dependent attributes. So at this point, most of the nominees have been eliminated. And so here's our second normal form conversion results. So now we have 3 tables now that came out of this one. We still actually could come up with 4 or 5 from this one as to if we go into BCNF format actually. But now we have 3 tables because we took out all of the keys and we put the keys into a separate table. So the table number 1 is the table of projects, where we have 15 and we have evergreen and we have 16 and we only have 1 of each project. So we got rid of the repeating groups and we got rid of the partial dependencies by creating a new table. Now we have a table employee. We just got rid of, in step 2 we just got rid of partial dependencies. In step 3 we get rid of transitive dependencies. And in removing those partial dependencies we end up making more tables. So in this table here, we've got rid of the partial dependency, but we still have a transitive dependency going on here because the job class should be determining how many hours are charged, but the hours of charge are being determined by the job class, or is it the job class that's determined? Is there a relationship? There's really no rule that says there is. So we actually have to make this into a rule. The trick to all this, you fix it by making keys. So you make a key to get rid of partial. Oh, we have attendance. So let me pause this for a second. Okay, so now that we have the attendance out of the way, let me finish this here. And for those of you who just showed up, I've been reviewing normalization in preparation for the final exam later today. You will have questions on normalization. You will have more than 1 question on normalization. So this is actually something you do want to pay attention to. All right, so what do we have? We've gone from first to second. We got to second by removing those partial dependencies. We removed the partial dependencies by making the keys really keys. Taking all of the keys, the primary keys in the tables, and separating them out into other tables. Can you please not talk while I'm talking? Thank you. So what we have here is the first table, which is called project, and it has a primary key along with a name that's associated with a project number, as I mentioned before. This will give us a full dependency versus a partial dependency. We still have a problem in here because we haven't gotten rid of the transitive dependency, which is a nature of third normal form. So we're in second normal form because we have transitive dependencies by definition. And in the assignment here, well, we actually have 2, which is not your most optimal design. And we can actually improve this a little bit further, but this is not a third normal form characteristic. This is a BCNF characteristic, a BNF characteristic, excuse me. So employee number and project number, when we have multiple dependency, a key that's dependent on a key, not such a good idea, but it's still second normal form. And then we have assigned hours that might be assigned to it. So second normal form means that we are in first normal form. You cannot be in second unless you're in first. And it includes no partial dependencies. And there are no attribute that is dependent on only a portion of the primary key. So all of there's only 1 15 and only 1 name here, and then this number here is going to be used down here. So we can have the same consistency. So let's put this into third normal form, and so now we can get rid of that transitive dependency. So we're going to identify each new determinant. Oh, you guys missed attendance. Oh well. So for every transitive dependency, you're going to write its determinant as a primary key for a new table. So as a determinant, we're actually going to make keys where keys didn't exist to get rid of those transitive dependencies. So a determinant is any attribute whose value determines other values within the same row. And here's our determinant here, going back to refresh your memory on this one here, where job class determines the charged hours. So this was never identified as a key. It turned into a transitive relationship because if we say like job class A, B, C, A is $10 and B is $20 and C is $30 or something, then we could have a really bad design here if we have A and some people are making $5 or A and some people are making $50 when the class A is supposed to be something else. So we get rid of this transitive relationship, and that's really a good definition of the transitive dependency as well. When a job class is dependent on, when the rate of pay is dependent on a job class. So we're getting rid of identifying the dependent attributes so we can take them out of the table, identify them as we did in step 1, identify the dependency, and then name the table to reflect its contents. So what we're doing is removing the transitive relationships. So we remove the dependent attribute from the transitive dependency, eliminate all of the dependent attributes in the transitive relationship for each one of the tables, draw a new dependency diagram if we want to show the steps 1 through 3, and then check the new tables and modified tables in step 3 to make sure that we have the determinant that does not contain inappropriate dependencies. So here is our third normal form database, no partials and no transitive dependencies. What do? We just pulled the job class out. So now we have same 3 tables, originals, and then this one got split into 2. So we have job class and charged hours. So all of our job classes have the same charged hours, and we have no partial, and we have no, well, it depends on the job class. No, it depends on the hours. No, it depends on the job class. We have a stronger fit between job classes and hours being earned per job class. And then we put job class over here. We made a foreign key out of it over here to make sure that we can link up the employees with the job classes. So that was the conversion from first, second, and into third. And this is sort of the second time through this lecture, so I'm kind of going a little bit faster through it. We covered this in the second weekend. So the third normal form is in third normal form. If it is in second normal form, if it's in second normal form, it's also in first normal form. So third normal forms are in first, second, and third. It's not just third. And it contains no transitive dependencies. We can take a second, put it back into a first. We can take a third, put it back into a second. It's more commonly seen for a third to go back into a second. Why do we want that? Because we have to do a join here. So if we have to do the join, depending upon how many job classes we have and how many employees we have, that might be slow. We could easily put this back in here, make it into a second normal form database, and make the query run faster. So a lot of the conversions that go backwards from third to second are done that way for efficiency purposes. So we can also improve the design even further. Did you have a question?
Yeah.
Okay.
So is it for the job class, is it like for one job, it always refer to one charge hour?
Mm-hmm.
But for one charge hour, it can refer to like many jobs, right?
It could. If you had job class A, B, and C, A and B could both be $20 an hour, and C could be $30 an hour.
Oh, and then for the partial relations, it's the opposite, right? I mean, for one project number, it's
when there's a transitive relationship, there's no dependency. Let me go back up to here. There's no, this transitive dependency, there's no key. There's no dependency. It's transitive. So if the $30, we don't know if the $30 an hour makes them job class A. We might have one person makes $30 an hour who's in job class A, and when the other person is in job class B.
I mean, yeah,
and we don't know we don't know that B leads to $30. We could have a B. We could have 2 B's in here that are 30 and 1 B in here that's 10.
Right.
That's allowed. Because it's transitive, which means this one depends on this one depends on this one, and there's no clear relationship going on.
I guess my question is, how do I make sure that during the second normal form, I don't convert the transitive dependency in that step?
You could.
Okay.
Then you'd be automatically from first to third. You don't have to go into second.
Okay, so we don't need to show the...
No, not even in the assignment. I told the class when we went over the assignment last time, the one that was, I think it's number 4. I can't remember. Number 4 or number 5, I can't remember. But you just give me the end result. Because some people will go from first to third, skip second. I would go to first to third and skip second because I'm going to look at this and go, oh, that should be another table. I'm going to look at this and go, job class, wait a minute. Why do we have a job class? If we have a job class, then what does it mean? It means we're going to put people into classes? Then if that's the case, then I'm going to get rid of that transitive relationship. Because you could query this and go, okay, everybody who makes $30 an hour, you're all in the same class. But they're not. Only some of them are, which makes it partial. It's transitive because this one's determining this one and this one's determining this one. We don't know which one to look at first. So we could, if we can get rid of this relationship issue by making it clear, which is what we're doing.
Say that the charge tower cannot define the job.
In this table, one of them is determining the other. The other's determining the other one. We don't know which one is the key. Most people may actually look at charge tower and say that the people that are making the more money are in the higher job class. Who knows? Maybe it's the opposite. But then you have people in different job classes that are making different amounts of money, which is actually kind of interesting, yeah?
So there is only one difference between 2NF and 3NF, that we are just removing transitive dependency?
Correct.
That's only one difference.
Correct. Yeah. That's if you could be in second normal form if you have transitive dependencies, you're in second normal form. If you have both transitive and partial, you're in first normal. If you don't have either one, you're in third normal. If you're in third normal, you still have further improvements that you can make. Let's see. Let's go look at that for a second. A lot of people like third normal, they'll stop there. But there's still problems with this. So third normal has no transitive dependencies. So you can improve the design even further. And so if you improve it even further, following changes were made to get us to where we are now. We now have primary key, naming conventions, attributes, atomicity, they're all the same. We added some attributes, we added the relationships, we redefined the primary keys, maintain historical accuracy, and we're using derived attributes now. So our complete database sort of looks like this. If we were to implement it, we'd get a really nice table design out of it, actually. And we can get pretty good data results. So we do have a situation where we might end up with duplicate entries for job titles. So duplicate entries for a job title table is an example where we have job code 511 and job code 512. It's the same job, but it's under two different codes. So a programmer and a programmer. Actually, we get this a lot with classes in a registration table. Long time ago, the class used to be called, SCN 980, and now it's called SCN 981 or CEN 981 or whatever now. Not this class, another class. Actually, that's a true example. And it's all the same description, it's all the same class, but there's two different class codes for it. That means we're not in BCNF format. That's a characteristic that can be removed if we go into BCNF format. So BCNF is just another add-on for the third normal form. Third normal form, just to reiterate the point, there's no partials and there's no transitive dependencies. Obviously no repeating groups either. BCNF, there's no case where we could have multiple job descriptions that belong to the same job number, or different job numbers, I should say, that have multiple job descriptions. We can't have programmer in here twice with two different job codes. So how are we going to remove that? Well, then we can find another determinant. So every determinant in the table is a candidate key. So Boyce-Codd normal form, BCNF, there has some characteristic where we don't have these, it's not a repeating group, it's basically, it's a better enforcement of the key, makes it stricter. So if we look at every candidate in there as every determinant as a possible candidate key, then we're going to identify more keys where we don't necessarily need to. And we're going to key it out even further, which means we're going to pull the data out even further. So it's the same characteristics as a primary key, but for some reason not chosen to be a primary key, which means usually if we have more than one primary key in that table, we're not in BCNF. Because BCNF says we only have one. one possible way of searching that table in terms of that key attribute. So if a table contains only one candidate key and third normal form and BCNF are equivalent, BCNF can be violated only if the table contains more than one candidate key. So we're not in, ITU probably is not in BCNF if we're storing social security number along with visa number along with student ID number. We're not in BCNF. We have more than one candidate key. The reason why we care about BCNF is if we search the table on social security numbers, we're going to get a different count. Maybe we'll find you, maybe we won't find you. If we search it on student ID, where we're going to hopefully get everybody because everybody has a student ID. If we have a visa number, depending upon the number, we may or may not find you, depending upon what's going on with that. So most designers consider the BCNF normal form as a special case of third normal form. And a table that is in is third normal form. If it is in second normal form and there are no transitive dependencies, a table can be in third normal form and not in BCNF. If a transitive dependency exists when a non-prime attribute is dependent on another non-prime attribute, we're going to make one of them prime. We're going to make one of them primitive. So a non-key attribute is the determinant of a key attribute. So here's our table that is in third normal form but not in BCNF, which is the one we just looked at a few minutes ago. Actually, no, this is another example where we have A and B and C and D, where B and C have a relationship, A and B have a relationship, and A-B combination has a relationship with C and D. So what we do is we just make another table out of this. We switch them into two. So we decompose this. So here's the one we originally started with. This is the first normal form of the A, C, B with a partial dependency on C and B. So now we have third normal form and BCNF if we have A, C, and D, and then we have C and B. So instead of putting all the data into one table, we separated it out into two tables to enforce the integrity of the key. And we created a new key where another key didn't exist. So we made it a full instead of a partial dependency. Most people aren't going to do this because it makes the database hard to search. If you're in BCNF, you have more reliable data for the most part, but your queries are slow. What's wrong with just enforcing some business rules and having your third normal form? Third normal form is not perfect either, actually. We have fourth and fifth and sixth and eighth, and it goes up to, I don't know how many normal forms there are, but there's researchers that bring it up to fifth normal form. Fifth normal form database is extremely hard to query, hard to put together. Because as you're looking at it, you're getting rid of other things too. You're putting in constraints for case sensitivity. You're putting in constraints for how long the data fields are. All these weird things you can just kind of stick in there. A good question. Nobody does it. That's why everyone likes their normal form. No one's going to do it. It makes it hard to query. It makes it hard to put data into it. Has something to do with unique, where I think fourth normal form gets rid of the unique values. If something has to be unique, people do this all the time. They have one primary key, but everything else has to be unique.
But it has advantage of when you enter the data.
Yeah. What makes the data harder to put it in. The higher you get up, the harder it is to put the data in. Anything past third normal form is hard to work with, so everyone stops at third normal form. Because there's other things you can do to tweak it a little bit more.
If you go higher and higher normal
Yeah.
forms, the data entry becomes harder.
Yes.
Easier.
Yeah, it becomes harder. The higher the normal form, the harder it is to put data into the database, and the harder it is and the more time consuming and less efficient it is to query that data.
It's counterintuitive. Like,
It's counterintuitive, you're right.
In both fronts, like while we are making the reports or querying the database, it is more, more joins, more data.
Yeah.
And for the data entry also, it is.
It's more difficult. So a lot of people will stop at third normal form. They won't go any higher than that. A lot of people stop at second normal form. There's no law that says you have to have third normal form databases. Most of your online companies, if you have a database and it's populated already and it's in third normal form, you can actually convert it into a second normal form structure. Make it read-only because it's going to be read-only anyway if you're just using it to look up books and stuff. Just to look up like a inventory. Makes it faster to query. So you're going to get better performance out of the database. A database has already been populated with data. If you convert it, transfer the data, move the tables around, transfer the data around so it's all done correctly. Take a third, put it into a second, you'll get better performance out of it. And actually less storage makes the database smaller, easier to query, more efficient, faster running. Only problem is not so good for updating. If you're going to update it, then you're going to go back to a third normal form format for it. So what a lot of people do actually is put it in the highest normal form when you're updating it, getting the data in, and then reduce the normal form for application use. So if you're going to use it to query, then reduce it down to second normal form. No one's going to go into first normal form, but you go into second normal form by merging the data. Instead of doing the join on the table, go ahead and just put it all together. Or the other solution to this, which a lot of people do, and it makes a lot more sense actually, leave it in third normal form, create second normal form views, and use the views for the queries. Don't view the underlying table. So you're going to pre-cache the join, and you're going to query on the views, which makes it a lot faster. You're reducing the normal form with the views. You can still update a view. Actually, trivia question. When can you not update a view? Ah! Ding, ding, ding. Correct answer. You can only update a view that's based on a single table. If the view is based on multiple tables, you cannot update it. That's kind of stuff you want for the multiple choice questions, by the way. That was a very typical question. So that's like the format. When can you not do this? When can you not do that? Are there any restrictions on views? Actually, is another side tangent kind of question. Are there any restrictions? What are the restrictions on a view?
Only a particular user can see the left side of the view.
No. Anyone can see a view. You just give rights to it. You just give privileges to it. There's no restrictions on a view. Views can actually span multiple user accounts too. Views actually are just replacements in concept. The only restriction is memory. If you make too many views, you're running all the views. It's not really a restriction, it's efficiency. You got all your tables. You got a very small amount of memory left over. You make a bunch of views. Views don't exist. Views are abstract. When you query the view, then the underlying view needs to be created. You could fill up the memory and the whole thing could bomb out on you. Because you're looking at something that doesn't exist, and then you're writing a query on it, and then it has to exist when you run the query, so it's going to refresh itself, populate itself, and then run out of memory and die on you. So views, people don't think they take up any memory, and they don't until you run them. And then you might end up with, oh, well, when we run the views, the database works just fine, and we have 20 gigs available for us, and everything's working great, and we can query the tables, no problem. When we run the application, it just crashes out of memory constantly. What's wrong with that? And then you're like, oh, how many views are you using? What are you doing with those views? Because all of a sudden you're now creating twice as much data as you had before with those views. So then they'll go, okay, I don't want to use the view. Put it back into second normal form. So then you start playing around with the normal forms to make it more usable. So, well, actually you can protect a table so you can't update it just by changing the access rights to it as well. So. Alright, so here's our decomposition into BCNF, and BCNF is from the guy who made, why do they call them first, second, and third normal forms? I don't know. Normalization is fixing problems and normalizing the data. But BCNF is the guy's last name, so it's the author who actually created it. So, and then somebody arbitrarily came up with first, second, and third. So most databases are in third. Doesn't really mean that there's anything wrong with the database, actually. So here's some sample data for a BCNF conversion. We have a student ID, a staff ID, a class code, and an enrollment date. And so the student ID was staff ID. Well, they have different classes in here, and we have different classes that are associated. Here we have two. We have 125 student with 20. We have 144 student with 20, and both in the same class with different grades. So So another BCNF decomposition here is that we have a panel A, which is this first one up here. It's in BCNF, but not, it's in third normal form, but not in BCNF, where this is the table we're looking at actually. This is third normal form, not BCNF. So we turn it into BCNF by taking the class code and the staff ID out of there. Why? Because in here there could be a case in which we have a staff code, staff ID, a student code, or excuse me, a staff ID and a class code that may not match. So another trick to this is looking at this going, well, we have some duplicate information. So we have 20 and we have 32, 4, 5, 6. And we have 20 and we have 32, 4, 5, 6. Whenever you see duplicate information, you know it can probably be reduced a little bit further. What we don't want are two rows that look kind of similar. Like this row here and this row here are looking very similar. But it's different because people would argue it and say, well, look, the student ID is different. Yeah, but we could have a class code that doesn't match a staff ID. It could be 20 and we can accidentally put that in incorrectly. And the database would let us do it. So, and then people go, oh, just make it unique. You make it unique. You're actually, what you're doing with those unique keys is you're enforcing BCNF, but you're not saying that it's BCNF. And then you make it difficult to impossible because it isn't unique. This teacher is teaching this course. So what do you got to do? Change the course number? Which is actually kind of funny because then you see people do this in databases. They go A, B, C, D, E. It's like how people put in, you know, students with the classes they're taking. They put class number 1, class number 2, class number 3, class number 4, all in one table. And you go, well, they're stuck. They can take up to 4 classes. That's it. Or you see color 1, color 2, color 3, color 4. 4 colors? Or you see this where it says, you know, staff 20. Oh, she's also teaching a weekend class. Okay, -2. Because you can't have the same code in there twice. Because we don't know one's a weekday and the other one's a weekend. So we're not, IT is not in BCNF format. But anyway, long story short, they've made it unique enough to the point where you have to make up these special little numbering schemes and these special little codes to make it unique. Because someone made a requirement that it be unique. And we know that unique keys are not the same as keys. Why are unique keys not the same? What's one reason why the word unique is not the same as a primary or a foreign key? Oh, okay, now I can come up with 3. So, yeah, you're right. The nulls. Another one is unique doesn't enforce referential integrity. So you're right about the nulls. I wasn't thinking about that. You can't have a null. Actually, you can have a null on a unique key, but you can't have one for a primary key or for a foreign key. Unique keys don't enforce referential integrity, which means you don't have to have a matching primary to foreign relationship. And the third reason that I was thinking about was that unique keys are always indexed. Excuse me, primary keys are always indexed. Uniques aren't. So the search on a primary is faster. And the other day somebody actually said something that was kind of interesting. They said, well, we can't join the table because we don't have a primary key in there. I'm thinking you don't need to use a primary key for a join. You can join on anything. You don't have to join on primary keys. If you join on a primary key in a table, then you would have a faster join because it's going to join the index. Because primary keys are always indexed. So if you have a primary over here and a foreign over here, if you have a primary key, will always be automatically indexed. Most people would put an index on the foreign just in case you want to merge them together. And you're going to merge them together through a join operation. You'll make the join run twice as fast if they're indexed. Because you're not joining the tables, you're joining the indexes, and then you're retrieving the data out of the index. So faster, more efficient to put keys in there. Making something unique, yeah, it makes it unique, but it doesn't do anything for you. So, in fact, if anything, it can make it, you can put BCNF, you can put it into BCNF and then make it impossible for you to actually put the data in because it's unique. You say, wait a minute, the same teacher is teaching 2 sections of the same class, but you can't put it in. So you have to put in section 1, section 2, section 3, section 4. It's the same class, but now it's got different codes. So another one here, break it out. We have the class code with the staff ID. This class code is teaching this class, so we don't have duplicates. So, What I mean by duplicates is, we don't have repeating duplicate information, although the row is unique. The class code and the staff ID are sort of the same for these two over here. So, well, they are the same. They're also the same for the 25s as well. Oh, actually, it's kind of interesting. The 25 staff ID has got two different classes, it looks like. Yeah. Anyway, so normalization should be part of the design process. We put things in entity relationship diagrams so that we can guarantee that we're at least in second and possibly and hopefully in third normal form by the time we're done. And many real-world databases have improperly designed or burdened with anomalies of improperly modified during the course of time databases. Because we start out in third normal form and then someone adds something to it, and then somebody else adds something to it. And then by the time the database has been around for a few years, it's not in third normal form anymore. So a lot of, actually a lot of companies hire consultants to do this. So maybe you guys will end up doing this. There's actually a lot of money in this too, actually. You get hired on, you go into a company, you take their existing design and you fix it. The way you do that is you come in through and you design it fresh. You take a look at all the business requirements, all the database design. You create your own set of entity relationship diagrams. You put together your own design. You build your own tables. You take the old data and you put them into your new tables. And voila, you have a better working system. You fixed it. You improved it. And you made it faster. You made it more efficient. Or you took a look at their design and you went, oh, okay, I can fix this, I can fix that. And instead of redesigning it, you just backward engineer it. And you make it into a third normal form. And then you figure out, oh, this is too slow. Then you put it back into a second normal form to make it more efficient. So, but there's a lot of money in that, actually, because there's a lot of people, there's a lot of companies out there with bad databases. Because here's what happens with the database. You build the database, and you're the database architect, and you got this perfect database. And then along comes this application developer who has no idea what they're doing. He says, oh, I need a table that does this. And then the database, the DBA builds the table. And the table's got duplicate information in it. Because we already had that information over here, but you didn't know that it was over here. Or better yet, it's got mismatched information. It's keeping track of the employee's name and address and telephone number, or the customer's name, address, and telephone number, when it's already in a customer table. So it's duplicating the information. So now we got two versions of the same address. And then, lo and behold, maybe it's actually using a partial key dependency with something else. Oh, you bought this, here are all your customer orders. Because the guy who was originally writing the application didn't get full access to the database design, didn't understand it, or there was a component that was missing that the person needed, but the DBA didn't know where to put it, didn't know how to put it in there right. Because the person who's maintaining the database is not generally the person who designed it to begin with. If you're a designer who actually writes the databases, that does database architecture, you actually put the stuff together, you're going from project to project and you're not staying at a company that long to the point where you're maintaining it for the rest of your career. Then you wouldn't be designing anymore, you'd be DBAing, which is kind of a lower end position. So they hire all the junior people who just come out of school to be the DBAs. And then you get to work with somebody else's problems that happened before. It's like software engineering. When you build the program initially, it's at its best point. And then those designers are going to go away. They're going to build another software package. And then you're going to have maintenance programmers or junior level programmers come in to fix it. And the more they fix it, the more they break it. And the more the software doesn't work. To the point where you just rebuild it from scratch eventually. Which is what happens with databases. So it's the kind of same problem you get with software engineering, actually. The reality of it is there's more money in the maintenance than there is in the beginning. Because people don't spend money until there's a problem. In the beginning, they'll go cheap. They'll go, oh, can you just put it together? Oh, we have a database. Woohoo, it only costs us this amount of money. It's like, yeah, you get what you pay for sometimes, and here it is. And then they fill it up, and they use it, and all of a sudden, oh my God, our entire business assets, everything for the last 5 years is in this database, and it's not working. Now it's worth more money. So then they hire somebody who's really good, hopefully, who's worth the salary, hopefully, who comes in and fixes it and redesigns it for them. Because nobody's going to start out, give me the best database possible. You know, they're going to get whatever's affordable or whatever they can put together. And it's usually the IT guys that put it together to begin with. ITI, not database architects. So Anyway, the reason why we do entity relationship diagramming is so that we can create their normal form databases. It provides the big picture. Creates it through an iterative process. You can actually create it after the fact, so you can take a pre-existing database structure, create an entity relationship diagram out of it, and you're doing it for 2 or 3 purposes. One, actually this is a good trivia question, why are we entity relationship diagramming? Yeah, the no-brainer answer to that question is because we want to create a design for the database. But we create the documentation as well. We document what's in the database. We can take it and do an iterative development on it through entity relationship diagramming by testing it in the diagram before actually implementing it, testing it to make sure the relationships hold true and that the connections are all there, instead of waiting until we've populated it all full of data to find out there's a problem with it. So sometimes it's faster to solve problems with the diagramming technique. Also, it allows better communication between the developers and the application engineers, the ones who are building applications to work with this database. You show them an entity relationship diagram. They know which tables are there. They know where it's in. They may not necessarily know the exact field names, but they know enough information to know where to go looking for it, which is good. So, a lot of good things to entity relationship diagramming. People don't like to do it because they think it doesn't contribute to anything, or they think that it's too time consuming. It's kind of like doing proper software engineering. A lot of people won't come up with a requirements doc, won't do a design document, won't do any analysis. They just pick up a software package and start programming the solution. And you think about it and like, well, you could have saved yourself a lot of time and energy and mistakes by actually planning what you were going to do ahead of time. So the same concept applies towards databases as well. So anyway, for those of you who came in later may have missed it or want to read through it a little bit slower, that was lecture number 6B. And believe it or not, that was the second time through it. We covered this in the last weekend. But there's a good 30% of the final exams on this content area. So, because it's really the accumulation of all of the concepts of entity relationship diagramming, table creation, and database design. So it's the heart of database design, really. So I'm going to stop this capture.